Hi, I'm Jan, and I'll be presenting our work on the formal verification of high-level synthesis. Application-specific hardware accelerators are increasingly becoming more important in various industries. This is mainly because CPUs are not really ideal for every application. For example, a data center might use a CPU to send loads of stores to various different SSDs and hard drives, but this application doesn't use all the flexibility that the CPU offers. Instead, this means that it will introduce latency into the fetching of data, and it will also use a lot of power. An ideal alternative to this is to use an application-specific integrated circuit instead. This would produce the lowest latency and lowest power consumption, but it is very expensive to manufacture, and if the application changes in any way, the ASIC would have to be taken out and replaced. A good alternative to this is to use a field programmable gate array. This basically acts like reprogrammable hardware and can therefore be made application specific by programming a specific circuit onto it. However, if the application ever changes, one can reprogram the FPGA. So where does this flexibility actually come from? Well, FPGAs have two main components. They have lookup tables, which provide flexible logic gates, and they have configurable switches, which connect these lookup tables together. Both of these mean that one can basically program any circuit one wants to into the FPGA. Finally, there are also RAMs, which provide an interface to access data that they store, and this provides larger data for the FPGA, which can then be read by the LUTs. So how do we program the FPGA? Well, we need to program the LUTs, the contents of the LUTs, and how the programmable interconnects connect to each other. And this is done by using a logic synthesis tool. And designers normally write hardware in a hardware description language, which is then passed to this tool. This allows the designer to have fine control over the hardware, but it does take a really long time to design this hardware, and it takes a really long time to actually run the hardware and to simulate it to check if one has made any mistakes. One possible alternative to this is to use a high-level synthesis tool instead to generate the hardware. This allows the designer to actually write C code and software code, which is then translated into hardware. And this means that it's much faster to design hardware because one can reuse the whole software ecosystem, but one has less control over the hardware itself. And testing can also be much faster that way because one can just compile the software onto a CPU and run it there before generating the actual hardware out of it. The main research in HLS tools has been to try and make them produce faster hardware. However, if one performs a lot of testing in software, one would also want the HLS tool to be quite reliable so that one doesn't have to retest the hardware again once the translation is completed. So this is our main motivation for formally verifying high-level synthesis, because most HLS tools are actually quite unreliable in practice. So we fuzzed various HLS tools shown below using simple random test cases that were tailored towards HLS tools, and we found that all of these HLS tools had runtime errors. So our solution to this is to actually use ComCert as a front end, and then add a hardware backend to it. This is done by branching out at the 3AC stage, also known as RTL in ComCert literature, although this clashes with a hardware term as well. So we call it 3AC. And we translate from 3AC into HTL, which is a hardware-specific intermediate language, on which we can perform some hardware-specific optimizations like RAM insertion. From HTL, we then translate into proper Verilog code. Currently, we support all control flow, integer operations, non-recursive function calls, and local arrays, structs, and unions. Now I'll go over a quick example of a translation. So given this C code on the left, quite simple, just some loads and stores to a tiny array, ComCert will generate the 3AC code shown on the right, which in this case is non-optimized, and 3AC is basically just a control flow graph representation of the program where each node is an instruction. And each instruction then links to the next one. Now looking at a quick overview of HTL. So HTL is a representation of a finite state machine with data path. And it is therefore mainly composed of a data path map, which maps from positive integers to Verilog statements, and a control logic map, which also maps from positive integers to Verilog statements. These are then combined in a larger module type, which is the top level type, where we have the data path and the control logic, but we also have top level registers, I/O registers, to be able to control the module, such as the reset register, which will basically reset the module to its initial state. In addition to that, we also have an abstract RAM specification, which we can then use to do optimizations like RAM insertion, which would then properly use the RAM without actually having to implement a RAM in HTL. So the translation from 3AC to HTL is basically a translation from a control flow graph representation into a finite state machine with data path representation. And so we translate the control flow into a finite state machine. Then we also translate all 3AC instructions into equivalent Verilog statements. And we transform the call stack and translate that into a Verilog array. Pointers which are passed to loads and stores are then translated to direct array accesses and to addresses into that array. And the main difficulty with this translation and the proof of this translation is that we actually need to translate byte-addressed pointers into word-addressed array addresses. So once we've got HTL, we can perform some slight optimizations on the HTL code. So the main one being proper RAM inference, so that we get low area usage on the FPGA, because a lot of the large data can just be put into the special RAM blocks. So this is done by basically translating direct accesses to the stack array, and these become separate signals into the abstract memory RAM, into the abstract RAM block that we have in HTL, and we then control the signals to be able to perform the same operation. So in this case, we're loading a value from reg5 divided by 4. So to do this on the RAM, we first enable the RAM, then we say that we want to perform a load, and then finally we give it the address from which we want to load to. And then on the next clock cycle, the result of that load will be available. So now the translation from HTL to Verilog is basically more of a syntactic change. Most of the Verilog statements actually stay the same. But one thing we do is actually implement the RAM interface in Verilog itself, and we prove that it behaves properly according to the specification that we have. So one thing to note is that this RAM implementation is actually given by the logic synthesis tool authors, and one has to actually stick to this syntactic construct so that the synthesis tool actually recognizes it and implements it as a proper RAM. And so the data path map is translated to a case statement where where it maps from also the state to the Verilog statement it should execute. And so here we can see all of the explicit loads and stores from memory that use the RAM interface that we implemented before. And then finally, the control logic map is also implemented with a reset state, which will set the initial state of the module, and then just a case statement, which describes a state machine that just describes how the next state that the state machine should go to. So now for how we actually do the verification of the translation. So first, looking at the semantics that we use. So we use a small step operational semantics that we adapted from Leuf et al. From 2019. And the main idea behind these semantics is that the top level of semantics is basically a small step semantics where every clock cycle is one small step. And so at every small step, we actually then perform a big step and execute the whole module in one go at every clock cycle. So now just to look at some main challenges that we came across in the proof. So the main difficulty in the proof was actually translating the memory model from a more abstract and infinite memory model that Comcert uses to a much more concrete and especially finite RAM that we then implement in Verilog using these control signals to control the RAM. And so some other difficulties were that we also need to translate the byte addressed memory model into a word addressed memory model for performance reasons. And in addition to that, actually integrating Verilog semantics into Comcert in the first place is not that straightforward, because Comcert makes assumptions over the top-level execution of intermediate languages. And it says that there are at least 3 states that the intermediate languages should have, such as a call state, a return state, and a main state. And these don't really have a equivalent version in Verilog, so they need to be artificially implemented in some way by using internal registers to do that. So, for example, the call state will basically set the reset high so that the module will start in the in a known state. And so then abstract values like the program counter need to actually also correspond to values in explicit values in the registers in Verilog as we execute the whole module in one go. So now looking at some results. The bad news is that with division, we're approximately 27 times slower than existing HLS tools. In this case, we're comparing against LegUp, and we managed to execute the whole 27 out of 30 of the Polybench programs, where the 3 last ones were floating points, and so we couldn't handle those. But those are shown on the bottom, and the green bar then is how Vericert compares to optimized LegUp. And on average, we're 27 times lower than that. Then the orange and blue bars represent lower optimization levels of LegUp to show how we compare against that as well. The top graph then shows execution time relative to LegUp, which we can see here is quite poor because we have divisions. And the bottom graph shows area, which is actually not that bad. And the reason we're actually 27 times slower with division is because we implement division in 1 clock cycle. And as division is a long operation, this means that it really bounds the upper limit of the maximum frequency that our FPGA can actually run at. So our whole execution becomes much slower. The better news, though, is that without division, we're only about 2 times slower to optimized LegUp, and we're actually on par with LegUp without any optimizations, which is quite encouraging. And so in this case, we actually did the test by implementing division in terms of shifts as C code. In addition to that, we also fuzzed Vericert using Csmith, just like in our study of the other HLS tools. And ideally, we'd find that Vericert has 0% runtime errors. However, in practice, this was actually not the case. Interestingly, we actually found a small bug in the trusted codebase of Vericert, where we were using the wrong operator in the pretty printing. But once we fixed that, we did actually get no runtime errors on the fuzz run. So as a conclusion, we've written a formally verified high-level synthesis tool in Coq based on Comcert, and we've proven the translation from 3AC in Comcert to a proper Verilog as a state machine. We implemented a small optimization like RAM inference or RAM insertion in the HTL pass, so that our area usage is close to the area usage of existing HLS tools. And performance without division is actually comparable to LegUp without optimizations, which is very encouraging. However, we do have a lot of future work that we want to implement. So the main one being the implementation of scheduling and resource sharing, which would also fix the problem we're currently having with the division operator, and it would allow us to execute the division over multiple clock cycles instead. We would also like to add external module support for easier function calls. And finally, we would also like to add global variable support just for more, to be able to support more input programs. Thank you.